Okay. In first class, we discussed different opamp topologies. Then we have seen single-ended opamp and fully differential opamp circuit and its diagram and its gain equation, etc. Okay. So what is the difference between that differential opamp and single-ended opamp? In the case of differential opamp, the output swing is double as compared to single-ended opamp. Okay. So next in this video, the second video, we start with again the discussion of one-stage opamp topologies, and we already discussed that in one-stage opamp topologies are again classified into two types: telescopic opamp and folded cascade opamp. Okay, so here we start with telescopic opamp. Okay, so telescopic opamp. So we start our discussion. Here we discussed telescopic opamp, and the discussion start from our previous structure. So the previous structure means, in the case of the previous structure is our single-ended opamp. Okay, so this is the previous structure, that is the single-ended opamp. So from this structure we develop the structure for telescopic opamp. Okay, so in the case of single-ended opamp structure, it is a differential amplifier with PMOS load. Okay, so in order to increase gain of this structure, this single-ended opamp structure, what is the method to increase the gain? So in order to increase the gain, we adopt the method is cascoding, not cascading, it is cascoding. Okay, so this using that method we can increase the gain. Using cascading method we can increase the gain. So increase the gain means by extending the structure by cascading. Okay, so from the previous structure, that is the structure of the structure of the single-ended opamp is extended to increase the gain by cascading, result in telescopic opamp. Okay, so telescopic opamp. So telescopic opamp, we want to increase the gain from single-ended opamp structure. For that we extending the structure by cascading. That is our telescopic opamp. So the right-sided diagram structure is the telescopic opamp structure, and left-sided structure is our single-ended opamp. So we develop the telescopic structure from this single-ended opamp structure by extending the structure by cascading. So what do you mean by cascading? Okay, so cascading means we provide cascade for both input pair and load pair. Okay, so if we consider our single-ended opamp structure, there are one section is our input pair and the other section is our load. That is, the transistor M1 and M2 is our input pair and M3 and M4 is our load pair in the case of single-ended opamp structure. Okay, so cascading means that provide cascading for both input pair and load pair. Okay, so if we cascade means cascade the pair with same structure, same type of transistors, same type of transistors. That means here the input pair is NMOS. In the case of single-ended differential opamp, single-ended opamp, the input pair is NMOS transistor. So it is cascaded with the same NMOS transistors. Okay, so the load is our PMOS. So it is cascading with the PMOS transistors. That is the cascading. So cascade the input pair and load pair with the same type of transistors. Okay, so if we consider the telescopic op-amp structure, the first we consider the input pair. The input pair is M1 and M2. That is our NMOS transistor. It is cascaded with the same type of NMOS transistor, that is represented by the transistor M5 and M6. Okay, then the M3 and M4 are the load, that is our PMOS transistor. So it is cascaded with the same type of transistors, that is the PMOS transistor, and the same structure, that is the load is diode connected, M3 is diode connector. So similarly the M7 is also diode connected. Okay, so this is the telescopic op-amp structure. So the telescopic op-amp structure consists of input pair. That input pair is cascaded by the same NMOS transistor, that is the transistor M5 and M6. Then there is a load structure, that is M3 and M4. It is cascaded by M7 and M8. So the four parts: input pair, cascade for input pair, cascade for load, then load. This is the structure of a telescopic op-amp. Okay, so the green color transistor represent the cascade structures. That is, one is for cascade for load and other is cascade for input pair. The blue color represent the input pair and load pair. Okay, so here the structure is extended. That is, the single-ended op-amp structure is extended by cascading, result in telescopic op-amp. Okay, so next we go for the gain expression for the telescopic op-amp. Gain expression for telescopic op-amp. So how to find the gain expression for telescopic op-amp? Okay, so we already know that the gain is equal to AV is equal to GM into R out. So we want to find GM and R out. Then only we can find the gain of the telescopic op-amp. So how to find GM? Okay, so to find GM, first we ground the V out terminal of telescopic op-amp. Okay, and mark I out. Ground the output terminal and mark I out. Okay, then find GM, capital GM, that is equal to I out by VID. I out by VID. So how to find I out by VID? So first we want to find what is I out of this telescopic op-amp structure. For that, consider the input voltage as VID, that is the differential voltage applied between M1 and M2, that is our input pair transistor. Okay, so what is the current flowing through the transistor M1? What is the current flowing through the transistor M1? So the current flowing through the transistor M1 is, the voltage applied to the gate terminal of M1 is plus VID. So the current flowing through M1, we can write it as GM into VID by 2, because the VID is the differential input. The half of VID is applied to base of transistor M1 and the other half is applied to the base of the transistor M2. If M1 the voltage is plus VID and M2 the voltage is minus VID by 2. M1 it is plus VID by 2, M2 is minus VID by 2. So the current flowing through the transistor M1, we can write it as GM VID by 2. Okay, so this same current will flows through the transistor M5, M7 and M3, that is GM by VID by 2. So it is a current mirror structure, that is M3, that is M4, it's a load, that is a current mirror structure, and M8 is also current mirror structure. So the same current will flows through M4, M8, that is GM VID by 2, and it is also same the current that flowing through M6 also. And what about the current flowing through M2? So M2 the base voltage is minus VID by 2. So the current flowing through M2 is minus GM VID by 2. Okay. So if we consider the terminal shorted to ground, okay, and apply the Kirchhoff current law. One current is GMVID by 2 and the other current is minus GMVID by 2. That is M2 current. That is also same as that of the current flowing through M6. Okay. So minus GMVID by 2 and plus GMVID by 2. So according to Kirchhoff current law, the output terminal that is marked as I out, the current I out is equal to GMVID by 2 minus of minus GMVID by 2. So that is equal to 2 GMVID by 2. So it is finally equal to GMVID. So I out, we can get I out is equal to GMVID. Okay. So capital GM is equal to I out by VID. So GMVID divided by VID is equal to GM. So what is that GM? GM means the input transistors. So that is input transistors. So GM 1, 2. We can write it as the GM as GM 1, 2. Okay. Then next we want to find the output resistance R out. So how to find output resistance R out? Without drawing the equivalent circuit, we can find the output resistance directly from this circuit. How to find? Okay. So in order to find that output resistance from this circuit, we consider M2 and M4 are initial transistors, that is output resistance. So it is a single ended, so we consider only one side, the output side only. So M2 and M4 are the initial transistors, that M6 and M8 are cascading transistors. So M2 and M4 are the initial transistors. So its output resistance is, we know that RO2 parallel RO4. Okay. So now we have two cascaded structures, that is M6 and M8. Okay. So that cascaded transistors, its resistance is included in the intrinsic impedance of the cascade device. Its resistance is included in the intrinsic impedance of the cascade device. So that is GM6RO6 and GM8RO8. So we can write the total output resistance is equal to RO2 into GM6RO6 parallel RO4 into GM8RO8. So RO2 and RO4 are the initial transistor resistance and GM6RO6, GM8RO8 are the intrinsic impedance of the cascade device. So we can write the total total output resistance is equal to RO2 into GM6RO6 parallel RO4 into GM8RO8. So finally we get capital GM and R out. So finally we can write the gain AV is equal to GM into R out. So we can write minus GM 1, 2 into RO2 into GM6RO6 parallel RO4 into GM8RO8. So this is the gain of a single-ended telescopic opamp. Okay. So what about the output swing of this single-ended telescopic opamp? So output voltage swing. So output voltage swing we can write it as VDD. So that is VDD minus overdrive voltage of transistor 4, that is VOD4. So it is a PMOS. So we take the modulus. So VDD minus VOD4 minus overdrive voltage of M8. Again it is a PMOS transistor. So we take the modulus VOD8 minus overdrive voltage of M6. So it is NMOS transistor. So minus VOD6. Then the M2 VOD2 Then what about our VOD9? So that is our current source. That current source is replaced by a transistor that is named as M9. So it is VOD9. So the output voltage swing of single-ended telescopic op-amp is VDD minus modulus of VOD4 minus modulus of VOD8 minus VOD6 minus VOD2 minus VOD9. Okay, so this is the output voltage swing of a single-ended telescopic op-amp. So we find the voltage gain. So we find the gain of the single-ended telescopic op-amp and also the output swing of the single-ended telescopic op-amp. Okay. So next we comes to the fully differential telescopic op-amp. So we already discussed the single-ended telescopic op-amp. So how to convert that single-ended telescopic op-amp into fully differential op-amp, fully differential telescopic op-amp. So in the previous class we already discussed this conversion. How to convert a single-ended op-amp into fully differential op-amp. Okay, single-ended op-amp, the structure is, it is a differential amplifier with a PMOS active load. Okay, how to convert that single-ended into fully differential? Fully differential means the output have two pins, V1 and Vout1 and Vout2. So for that the first step is remove the diode connection. Second step is bias the transistor with a separate voltage that is named as V bias. Okay, that is the step to follow for the conversion of single-ended to differential. So the again method we can apply here also. Okay, so how to convert the single-ended telescopic op-amp into fully differential telescopic op-amp? If we consider the structure of the single-ended telescopic op-amp, Okay, this is the structure of a single-ended telescopic op-amp. So we want to convert this single-ended telescopic op-amp into fully differential telescopic op-amp. The first step is remove the diode connection. So remove the diode connections from the transistor M3 and M7. Okay, then bias the transistor with a separate bias voltage named as VB. Okay, so this is the structure of a fully differential telescopic op-amp. So we remove the diode connection. Okay, and we bias the transistor with a separate bias voltage that is named it as VB3, VB4. Okay, so this is a fully differential telescopic op-amp. The structure as compared to single-ended, the only difference is we remove the diode connection and bias the transistor with a bias voltage. So the transistors are named as M0 is the current source, then M1, M2 as the input differential pair, and M7 and M8 are the load device, and M3, M4, M5, M6 are cascade devices. That is M3 and M4 for cascade for input differential pair, and M5 and M6 are cascade for load devices. So this is the structure of a fully differential telescopic op-amp. Then what about gain of this structure? Okay, the same method we can use here, but only difference is here we want to consider both the output sections. Okay, we want to consider Vout1 and Vout2 sections. In the case of single-ended op-amp, we consider only one section. So only one output pin, that is Vout1. Okay, but here it is fully differential, so that consists of two output points, Vout1 and Vout2. So in order to calculate the gain and output voltage swing, we want to consider both sides. Okay, so same method. So we already know that the voltage gain is equal to GM into R out. So we already find what is GM in the case of single-ended telescopic op-amp. So what about GM in the case of single-ended op-amp? single-ended telescopic op-amp? GM is equal to GM1, 2. Okay, the same value is also applicable in the case of differential op-amp. Say minus GM1, 2. Okay, then what about the output impedance? Output impedance are out. In the case of single-ended telescopic op-amp, in order to find output impedance, we consider only one side, because in the case of single-ended op-amp, only one output, V out to 1. But in the case of fully differential telescopic op-amp, in order to calculate output impedance, we want to consider both the sides. That is, we want to consider V out 1 side and also V out 2 side. Okay. So what is the output impedance? Okay. So output impedance. So how to calculate the output impedance? Here the initial transistors are M1 and M2 and M7 and M8. Okay. So its impedance is R1, 2 and R7, 8. Okay. Then the intrinsic impedance of cascode device. Okay, intrinsic impedance of cascode device means in the case of input differential pair, the cascode device is 3, 4. So its intrinsic impedance is GM34, RO34. Okay. In the case of load device, its intrinsic cascode for load device, its intrinsic impedance is GM56, RO56. Okay. So the total output impedance is RO12, GM34, RO34 parallel RO78, GM56 into RO56. Okay, so that is the total output resistance. In the case of single-ended, the output resistance is RO2. Only we consider only one side, that is only the right side. So we consider RO2, GM6, RO6 parallel RO4, GM8, RO8. Okay, so if we consider the fully differential telescopic op-amp, consider both the sides. Okay, so the initial transistors we want to consider M1 and M2 and M7 and M8. In the case of single-ended, we consider only M2 and M4. Here we want to consider two sides. So M1 and M2, M7 and M8. So the output resistance is RO12, then GM34, RO34 parallel RO78, GM56, RO56. Okay, so the gain of fully differential telescopic op-amp is given by GM into R out. So GM is the same as that of single-ended op-amp, that is minus GM1, 2. R out is RO1, 2 into GM34, RO34 parallel RO78 into GM56, RO56. Okay, so this is the gain of fully differential telescopic op-amp. Then what about output sink of fully differential telescopic op-amp? Output sink. So here also we want to consider both the sides. Okay, so in order to consider both the sides, the output sink is doubled as compared to single-ended telescopic op-amp. So output sink is equal to twice VDD minus VOD 7, 8. Say PMOS, so modulus minus modulus of VOD 5, 6 minus VOD 3, 4 minus VOD 1, 2 minus VOD 0. So this is the output voltage sink of fully differential telescopic op-amp. So PMOS we consider the modulus voltage. So the output swing of fully differential telescopic op-amp is twice of VDD minus modulus of VOD 7,8 minus modulus of VOD 5,6 minus VOD 3,4 minus VOD 1,2 minus VOD 0. Okay, so this is the output voltage C. So this is about fully differential telescopic op-amp. Okay, so next one we come to the drawbacks of this telescopic op-amp, disadvantages of telescopic op-amp. So the drawback of telescopic op-amps are the output sinks are relatively limited. Then the second one is difficulty in shorting the input and output, so difficulty to implement unity gain buffer. That is the most important drawback of telescopic op-amp. There is a limitation of using telescopic op-amp as a unity gain buffer because there is difficulty in shorting the input and output. So what is a unit gain buffer? What is a voltage follower op-amp? Voltage follower op-amp means according to our op-amp 741, the pin 2 and 6 are shorted. Okay, the pin 2 and 6 are shorted means the input pin and output pins are shorted. That is a voltage follower. It is known as unity gain buffer. So in order to configure a op-amp into unity gain buffer, we want to short the input and output. So if we consider a telescopic op-amp, there is a problem in shorting the input and output pin. So it is difficult to implement telescopic op-amp as a unity gain buffer. So next we check what is the problem behind in shorting the input and output pin of a telescopic op-amp. Okay, or we discuss the main drawback of the telescopic op-amp, that is the limited usage of a telescopic op-amp as a unity gain buffer. Okay, so cascade op-amp. It's a telescopic op-amp is also known as cascaded op-amp. Why? The op-amp structure is developed by cascading the transistors. Okay, so the telescopic op-amp is also known as cascaded op-amp. Okay, so cascade. So next we discuss how to use cascaded op-amp or telescopic op-amp as a unity gain buffer. There is a problem. Behind this. So we want to check whether this circuit, that is the unity gain buffer telescopic structure, can be used as a unity gain buffer. Okay, we want to check whether this circuit can be used as a unity gain buffer. So here we consider a single-ended telescopic op-amp and it is converted into a unity gain buffer. So in order to get a unity gain buffer, we short the input and output pin. So we short the output pin with the input pin, that is input pin means the base of the M2 and output terminal. So we short. So this circuit is a unity gain buffer. So next we check whether this circuit work correctly as a unity gain buffer. Okay. So if we short the input and output pin, we must make sure that the transistor M6 and M2 in saturation. Okay. Okay. So in order to short the input and output pins, we must make sure that the transistor M6 and M2 in saturation. Okay. So can you check the saturation condition of M2? Can you check the saturation condition of M2? So the drain of the M2 is marked as a potential Vx. Okay. So M2 in saturation. We check the condition for M2 saturation. So M2 is a NMOS transistor. So the saturation condition, we know that the VDS is greater than VGS minus VT. Okay. So here we consider the source is a common source. So it is treated as a 0. So VDS greater than VGS minus VT. We can write it as VD greater than VG minus VT. So if we consider M2, what is VD? VD is V. VD means M2. VD is Vx. Vx is greater than what is gate Vout. So Vout minus Vt. So we can write it as Vx greater than Vout minus Vt. So we can also write it as Vout is less than Vx plus Vt. Then what is Vx? Vx. We can write that Vx as the base of M6 is Vb. That is, gate of M6 is biased by Vb and gate source potential is VGS. Okay. So we can write it as Vx is equal to Vb minus VGS6. Vx is equal to Vb minus VGS6. Okay. So substitute the value of Vx in the equation of Vout. We can write it as Vout less than Vb minus VGS6 plus Vt. So we can also write it as Vout less than Vb minus VGS6 minus Vt. Okay. So this is the Vout. So Vout always less than the value of Vb minus VGS6 minus Vt. So the maximum value of Vout is Vb minus VGS6 minus Vt when M2 in saturation. Okay. So next we consider the transistor M6. So the saturation condition of M6. So again M6 is an NMOS. The saturation condition is VDS greater than VGS minus VT. So that is, we can write it as VDS M6. Okay. M6 the drain VDS. So we can write it as VDS. That is VD, that is our Vout. Vout greater than Vb minus Vt. Vout greater than Vb minus Vt. So the Vout must be greater than Vb minus Vt for M6 in saturation, and Vout must be less than Vb minus VGS6 minus Vt for M2 in saturation. So the maximum value of Vout is Vb minus VGS6 minus Vt, and the minimum value of Vout is Vb minus Vt. Vb minus Vt. So if we draw a line with a reference voltage Vb and another line Vb minus Vt. Okay. So the minimum value of Vout is Vb minus Vt and the maximum value is Vb minus VGS6 minus Vt. Okay. So maximum value is Vb minus VGS6 minus Vt. So the output always swing between Vb minus VGS6 minus Vt and Vb minus Vt. So the total threshold voltage is Vt, but the allowable range is less than 1 Vt. Okay. So the output voltage swing is allowed range is only between VB minus VGS 6 minus VT and VB minus VT. Okay. So allowed range, the output voltage, the output swing for the allowed range is less if we connect telescopic op-amp as a unity gain buffer. Okay, that is the output voltage swing is limited or reduced when we connected telescopic op-amp as a unity gain buffer. Okay, so generally cascaded op-amp or telescopic op-amp are not preferred as unity gain buffer. Not preferred as unity gain buffer. Okay, thank you.